So, work energy theorem and its applications. Okay, so we've been talking about work energy theorem here for a couple days now. Now I want to have you look at the reason why some things are the way they are. All right, you guys are all getting ready. Probably, I think maybe one or two of you already have your driver's license, but okay, most of you are probably getting ready to take your driver's test. So, question: what's the speed limit through a playground or school zone? 30. Okay, so we got to go 30 through a playground zone. The obvious answer to that is because children are present and they don't look always both ways before they run into the street. So that's why we have to go slowly to make sure kids are safe, right? The same sort of logic applies to why the speed fines double in a construction zone. Are there a lot of people present? Yeah, not children this time. Okay, but still, there's people in heavy equipment. They're crossing. They're near the road, crossing the road, whatever. Okay, so speed fines double. In my opinion, speed fines ought to double through a school or playground zone as well. Okay, those are areas where we're trying to protect people. Okay, so that's one of the reasons why the speed limit is so low through a playground or school zone, or in Okotoks in general. Just like it seems like half the town is now 30 kilometers an hour. Notice that? Like everything just seemed to drop. Yeah, it was 50, then everything was 40, and now over in that new area by Costco, it's 30. Everywhere is 30. Okay, so here's why though. Okay, it has to do with the work energy theorem. If I'm driving a car, let's say my car is 1,500 kilograms. Okay, and that, so we'll say mass is 1,500 kilograms. And what brings you to a stop in your car? Your brakes. Okay, how do they do that? Okay, they use friction, but what does the friction do? Okay, slows the wheels down. If I'm driving, even at the speed limit at 30 kilometers per hour, my car has what kind of energy? If I want to stop, what do I have to do with that kinetic energy? I got to get rid of it somehow, right? I have to convert it into something else or transfer it somewhere else, hopefully not to somebody running out in front of the car, okay? So that's what our brakes do. When we apply the brakes, they convert our kinetic energy into heat and sound. Okay, for the most part, even light a little bit. If you've ever watched night racing, okay, it looks really cool because when they apply the brakes before a corner, you can see these cherry red circles inside the wheels where the brake rotors actually glow. Okay, so it turns all of that energy into heat and sound and maybe a little bit of light. Okay, in either case, it's getting rid of it, right? It's turning it into something else so that I can do what? So I can stop. All right. Well, the only way it can do that is by having the kinetic energy of my car do work on the brakes, okay, essentially wearing down the pads and the rotors of the brakes, okay? So work is going to equal the change in the kinetic energy of my car. Everyone all right with that idea? Okay, so this force is the force of friction that my brakes can exert. D will be how far it takes me to stop. Okay, and on this side, we'll have the change in my kinetic energy. So that'll be 1/2 mvf. Whoa, the f goes down below. Okay, mvf squared, okay, minus 1/2 mvi squared. What do I want this to be? Right, I want that to be 0. So I'm just going to get rid of it. Okay, I'm even going to get rid of the negative because at least at this point, it doesn't matter. So the work done on my brakes has to equal the initial kinetic energy of my car. All right, so if, let's say I'm actually going the speed limit, okay, my speed would be 30 kilometers per hour, which is 8.3 repeating meters per second. Let's say I have really good brakes. They can apply a force of, let's say, 8,000 newtons worth of force, okay, in stopping my car. Obviously, that force changes depending on road conditions, okay? My brakes can squeeze together all they want, but if the road doesn't have sufficient friction, they just lock and I slide, okay? Even if they're anti-lock brakes, it's still, you know, they're cycling through. There's still periods where you're sliding and where the tires are rolling and then you're sliding, okay? But we're gonna say these are perfect conditions. I've got lots of friction. Okay, if I wanna calculate how far I would travel in stopping from 30 kilometers per hour, I'm looking for D. Agreed? Okay, how do I get D by itself? Divide both sides by F. Okay, Jake, you got a question? I got rid of 1/2 mvf squared because it was going to be 0. I'm going to be stopping. My final kinetic energy would be 0. No, I'm saying how far would it take me to stop? Not how far. Yeah, I want to know that I am stopping. Okay, so now I've got my formula set up. I can calculate how far I would travel under ideal road conditions, okay, in stopping from 30 kilometers per hour. All right, so D is going to equal 1/2 times the mass of my car, 1,500 kilograms, times the initial speed of the car, 8.3 repeating meters per second, and that obviously has to be squared because that part of the formula is squared. All right, and then I'm going to divide that by the force that my brakes can apply, 8,000 newtons. So 0.5 times 1,500 times 8.3 squared. Squared. Yeah, that's my repeating sign. Yeah, that's my repeating. That's the bar that goes over the number that says it's repeating. Yeah? Okay, that's how much energy, kinetic energy my car has in joules. Is that a lot? Yeah, I wouldn't want to step in front of it. Okay, there's a lot of potential to do work there. I just entered a whole bunch of them. Yeah, normally you just actually get the number calculated through, but I'm being lazy. Okay. All right, so there's the amount of energy that my car has. Okay, now I'm going to divide that by the force that can be used to stop it. All right, I'm going to travel 6.5 meters before I stop. Okay, so that's like from my desk to here at 30 kilometers an hour. That's at the speed limit. Okay, I'm not even speeding. No, just 1/2 times m times v squared. Okay. Yes. Under ideal conditions, my entire braking system, including the anti-locks, everything works perfectly. That's how far it would take me to stop. If it's at all icy, or like right now, you've got the sand that's on the road from the first snowfall, right? That interferes with your ability to stop when there's no ice, right? It's good when there is ice, but when there isn't ice, it actually causes you to slide farther, okay? Because you lose traction. What's that? When you've got that sand that's on the road right now, right? Because they put it on the road when it's icy. It helps you when it's icy for a couple of reasons. It first off increases the friction because there's the grit instead of the ice. Okay, but it also lowers the albedo of the ice. That is, it makes it darker and it absorbs more sunshine and melts faster. Then we also throw salt in there to accelerate that process even more. Okay, but right now with no ice on the road, we just have little pieces of gravel on the road, and actually that reduces the amount of friction under ideal conditions, right? Okay, so 6.51 meters is how far I would travel under ideal conditions in stopping. That's a long way if a kid runs out in front of you. Okay, 6.5 meters is going to seem like a long, long way. Okay, especially if they're only 3 meters from you. Keep that in mind. I am. I'd be slowing down, but this is a kid in a car. Well, it depends it depends how they fall, right? I mean, you still have energy. They're still very small. Mass matters. You got a big mass and a little mass, right? They could fall and hit their head, right? You could break, arm or leg. It depends where you get them, right? And so that's why we want to make sure we're going as slow as possible. Now, here's what I want to illustrate to you, because we all do this and we all justify it, and I hate it, okay? We always say, I'll just go 10 kilometers an hour over the speed limit, right? Because 10 kilometers an hour isn't that much, and it doesn't make that big a difference, except it does, okay? If I go 40 kilometers an hour, okay, this equation changes a little bit, okay? So 40 divided by 3.6 is 11.1 meters per second. All right, so now I'm going to do this same calculation, but now I'm going through the school zone at 40. Okay, so D will equal 1/2 times 1,500, same car, Okay, times 11.1 repeating squared, right, divided by same car, so it's still 8,000 newtons. So we'll have 0.5 times 1,500 times our answer squared. All right. There's the energy I had when I was going the speed limit, 52,000 joules. Here's the speed limit I have going 40, or sorry, the energy I have going 40. Almost, well, 92,500 joules. All right, now hang on. If I divide this now by my 8,000, okay, it's almost double. I'm only going 10 kilometers an hour faster. It's only a 25% increase in speed, but it almost doubles my stopping distance. Okay, so we're looking at 11.57 meters now. That's this whole classroom, the hallway, and a little ways into the lab. And that's only 10 kilometers an hour difference. Okay, the reason for that is this. Speed has an exponential relationship with kinetic energy, and thus the work required to get rid of it. So if I double my speed, how much further am I going to travel in stopping? 4 times. It's exponential. Okay? If I double my speed, I will go 4 times farther in stopping. If I triple my speed, 9 times farther. Okay? There's an exponential relationship between speed and stopping distance. That is something they do not teach you in driver's ed. I don't know why. It seems pretty important to me. Okay? They just tell you the faster you go, the farther it take you to stop. And that's just not quite right. Okay? It's not just farther, it's a hell of a lot farther. Okay? And here's the worst part of it. That 10 kilometers an hour saves you how much time? Not even. Okay? I'm going to use the Big Rock School Zone as an example. Okay, it's right down there by Big Rock School, obviously the cemetery, okay, and the big Ford dealership there. Okay, so that school zone is roughly 350 meters, roughly. Okay, it's somewhere in there. So it's 350 meters. Okay, long. So if I go the speed limit, okay, I'm going to go 350 meters. And, whoop, forgot the 0. Okay, divided by 8.3. All right, it's going to take me 42 seconds to go through that school zone at the speed limit. Whoop, keep typing wrong. Saves me 9 seconds. Okay, saves me 9 seconds. Well, lots of people do. Lots of people go faster than that. I flashed my brights at a guy the other day who was approaching me at what had to have been 70 through that very school zone. Okay? Because you go through that, you come in from out of town. Like, that's one of the worst ones, right? You're coming in from out of town, although it's been 50 for like 2 kilometers already. Okay? But you're on that road where there's nothing, right? There's houses on the north side and nothing on the other side. Okay? And people don't always slow down for that. And the main crosswalk that kids use is right there. Okay? For Big Rock. Okay, Big Rock Elementary. Yeah, that one. Okay, so what we're saying, guys, and this is the part that makes me so angry when I see people do it, is we're saying that some poor kid's life is worth less than 9 seconds. Okay, when we make that decision, okay, and we sometimes make it, okay, but when we make that decision to go 10 kilometers an hour faster than the speed limit through a school or playground zone, we're saying 9 or 10 seconds in our life is more important than that kid's life, which isn't right. Okay, but that we have to understand the implications of our decisions, and that's one of them. Okay, that 10 seconds or 9 seconds is the difference between somebody having dinner as a family or planning a funeral. Okay, it's a pretty big deal. Okay, it's a pretty big deal. That's why we have speed limits like that in place. Okay, you have to obey those speed limits. Right? You're on the highway, there's nobody around, it's 110, you go 120. Okay, right? I get it. We all do it, right? It's a little less of a problem in that situation than it is when little kids can run out in front of your car. All right. There's your real world application. Think about that. You guys are getting your license. It's something to think about. Okay, especially you, Strachan, because you told me you'd go 60 through a school zone. It makes me angry. Okay. Okay, so give this one a try. We got a slingshot, but it's being aimed straight up in the air. So drawn back and aimed straight up in the air. Okay, it's drawn back 0.4 meters. Okay, so 0.4 meters with a force of 1,500 newtons. The rock reaches a height of 30 meters. What's the mass of the rock? Is work being done in this question? Okay, so let's quickly look at our givens here. Okay, so our givens are that we have this distance of 0.4 meters. We have a force of 1,500 newtons. Okay, we have a final height of 30 meters. And then it doesn't tell us this, but we have to assume that the initial height is 0, as the person would be standing on the ground. Okay, what's the mass of the rock? All right, what else do we know that we're not actually told? Gravity, right. Okay, so work is being done, and that work is going to change the potential energy of the rock, because it's asking about height here, so we know it has to be a potential energy question. All right, so that means then that force times distance, and I know I have to use that because I have both of those, okay, equals m times g times h final minus m times g times h initial. But this is what? Is 0. Okay, so we eliminated that. All right, so now I want to find the mass of the rock. So what do I do with G and H? All right, divide by GHF. All right, now I have M by itself. All right, now I just plug in and solve. So I have 1,500 newtons times 0.4 meters divided by 9.81 times 30. Okay, so 1,500 times 0.4 is 600, okay, and then divided by 9.81 times 30. All right, so it's a 2 kilogram rock, roughly.
So mass is always in kilograms.
Mass is always in kilograms in physics, yeah. If you get it given to you in grams, convert it to kilograms.
Are we measuring its mass going upwards? I mean, like, it should be the same, but like, wouldn't the acceleration of gravity be negative if it's going upwards, because it'd be like pulling down the rock?
It is, but we don't need to make it that because we're dealing with a scalar quantity of energy. Does that make sense? Yeah, and they would make the mass negative. And mass can't be negative because then it weighs less than nothing. Which, well, sorry, it doesn't. It would also weigh less than nothing, but it would also mean that it is less than nothing. You can't have a negative mass because mass is the amount of matter you possess. So maybe it's made of antimatter, which would present a whole different set of problems. Okay, yeah, it would destroy the slingshot, right, and anything else of equal mass around. Yes.
So our formula sheet only has EP equals MGH. So do we just know that it's MGH final minus MGH initial because it's changed?
Right, because it's changed, right. Yeah. Kilograms. Yeah, because it's mass, right? Okay, so they start out really easy. They're just like force times distance. Okay, like they're super easy to start with. And then they'll become more and more complex as we go along. Some will involve kinetic energy, some will involve potential energy, and some will just be F times D. Okay, and some will be more like what we just did. FD equals a change in energy. Okay, they'll just kind of progress as you go along. All right, so get started on those, and then if there's any questions, we'll go over them together. So for number 6, okay, this thing has 320 joules of kinetic energy. So they told us, here's EK, 320 joules. Okay, the mass is 0.02 kilograms. Okay, so it's a rubber band, and we're looking for V. All right, this is why I give you a mark for writing down your givens. Do I have any formulas that have those 3 things in them? Yeah, this one. Can I solve for V? Right, I have EK, I have M, the half's a given, so right, all I have to do is go take the half of M over here, Okay, and then square root. It's like they told me 320 joules worth of work was done to this rubber band. Wouldn't have been any different, right? If I said I drew it back and gave it 320 joules of elastic potential energy, how fast will the rubber band go? Well, it would still be the same idea, right? I know the energy that the rubber band has. Yeah. Okay, any other ones? 7? Okay, same idea. If I use a force on a bow, okay, so I've got a force here of 100 newtons. Okay, I'm drawing the bow back a distance of 0.29 meters. What speed? Okay, so looking for speed, will a 0.120 kilogram arrow leave the bow at? All right, so I have force, distance, m, and I'm looking for v, which means this has to be this type of a question. I'm doing work, and it's changing the kinetic energy of the arrow. Okay, so then I'm just going to go force times distance equals 1/2 mvf squared, so my final kinetic, minus my initial kinetic, which would have to be what number? 0, because it's sitting in the bow. Okay, so now I just have to solve for v. Right, same manipulation as number 6. Isolate v. Yeah, that making sense? Right, so always write down your givens. They'll generally lead you. If you don't get from the question where you should go, the givens should help you get at least the right formula to start with. Okay, so I just got to read it carefully. All right. Okay, it says the anvil has 10,000 joules of energy and it's perched, which means it's not moving, above the road. So what kind of energy does it have? Okay, so it has gravitational potential energy, 10,000 joules of it. Okay, we know its mass is 35 kilograms, and we know that anything to do with potential energy, G will be 9.81 meters per second squared. Yeah? Okay. I'm just trying to find out how far above the ground it is. I just solve for H. If there's work, if it's changing. There's no change here. It just asks us how much does it have at this spot, right? It didn't say he moved it from the ground to there or he moved it from here to there. It just said it's there, right? So it's asking us about an instantaneous situation as opposed to a work done over the course of time. Yeah? So on the next set there are. Yeah, this is more the simple work energy theorem ones. It's just here's energy, here's potential, here's kinetic, here's F times D. Right. Yeah, well, that's all you can write out. That's all you know. Yeah. 13? Okay, so we got this cliff. He's ascended 400 meters before deciding it wasn't a good idea, which is a little late. Okay. At that height, he has 2.55 times 10 to the 5 joules of energy. So if it's about his height, what kind of energy is this? It's potential. Okay, so his potential energy is 2.55 times 10 to the 5 joules. We know his height is 400 meters. So again, this isn't a work question. This is a what's the energy at this point question. Okay, so we're looking for his mass. Right, well, what other thing do we know? G, always know G, 9.81 meters per second squared. So it's just a matter of EP equals M times G times H, okay? And we divide everything but mass over, because that's what the question wanted. Okay, so mass will equal 2.55 times 10 to the 5, okay, divided by 9.81 times 400 meters. Okay, that bottom part will need to be in brackets to get the right answer. And that should come out to 65 kilos. Okay, everybody all right with that? All right, so the ones that are on this first sheet, like I say, are not necessarily work energy theorem questions. They're actually easier than the ones we've done. All right, they're just about an instantaneous point. Okay, just energy questions. Yep. Because there's no work, right? They're work energy questions if it's both. These are just energy or work. Okay, the big thing is write down your givens. from there, you should be able to tell what formula you have to use. And that is, again, why I give you a mark for writing down your givens. If you're ever lost, you should be able to figure out what formula is involved just by what you have.